Hello, everyone. Today we'll talk about the main results found in the paper titled A Hybrid Adaptive Control System for Arbitrary Ultimate Bounds with Applications to Multirotor UAVs. So, in the classical model reference adaptive control framework, the main sources of uncertainties that are considered are parametric uncertainties, matched uncertainties, and unmatched uncertainties. The limitation of robust methods of classical MRAC, such as techniques as the dead zone modification or the continuous projection operator, guarantee only ultimate boundedness of the tracking error, and the ultimate bound is not user-defined. Hence, it cannot be made arbitrarily small, and it is proportional to the upper bound on the unmatched uncertainty. Furthermore, if we consider hybrid systems, and hence the hybrid MRAC framework, additional uncertainties arise, such as the ones in the resetting events that characterize the plant dynamics. So the goal of this paper is to develop the first MRAC system that, despite the presence of unmatched uncertainties, guarantees asymptotic convergence of the trajectory tracking error to a user-defined neighborhood of the origin, meaning that the neighborhood can be made arbitrarily small, including the singleton zero vector. We'll build the controller step by step, starting from the two-layer MRAC framework. So, here we have the plant model, where the parametric uncertainties are grouped into the A and lambda matrices. Then we have the matched uncertainties, in the T transpose phi term, while, in this framework, the unmatched uncertainties are not considered. Then we have the reference model, which is the model we would like our plant to follow. We have the auxiliary reference model that helps the plant converge to the reference model before the transient of the reference model has decayed. Then we define the trajectory tracking error and epsilon as such. We have the matching conditions. We assume that these conditions hold, meaning that our plant is capable of following the reference model. This is the control law, which includes the adaptive gains, which come from the adaptive laws shown here, where P comes from the algebraic Lyapunov equation shown here. So, as previously said, we were not considering the unmatched uncertainties. Let's do that now. So we add the term xi of T to the plant. We consider the same reference model and auxiliary reference model, and we still assume the matching conditions hold. So we modify the control law, adding the psi of T term here. The adaptive laws and the Lyapunov equation remain unchanged. Here we have the psi term that has the typical structure of a variable structure controller, and from here we can see that if we would stop here, this framework could have two issues, which are 1. Chattering, because in the error-bounding control law there is a discontinuity around epsilon equal to 0. And then there's also the problem of the parameter drift of the adaptive gains. To take care of these issues, we make the previous controller continuous and robust. We have the same plant model, reference and auxiliary reference model, and same Lyapunov equation. We change the error-bounding control law psi to psi clamp. And we see that the psi clamp function is basically the same control law as the one shown previously, but the discontinuity has been removed thanks to this ramp saturation function. So this avoids the problem of chattering. While, to avoid the problem of the parameter drift of the adaptive gains, we apply the projection operator and the dead zone modification. The dead zone modification turns off the adaptive gains once the tracking error has entered a compact set around the origin that the user can set, while the continuous projection operator acts on the adaptive gains, constraining them in a convex set and acting only when the adaptive gains are between an inner threshold and an outer bound, and the derivative of the adaptive gains is pointing towards the outer bound. Hence, it constrains the adaptive gains to not go beyond the outer bound. In such a way, we avoid the parameter drift of the adaptive gains. To apply this framework also to hybrid systems, we consider the hybrid plant model shown here, where at the top we have a differential equation and at the bottom a difference equation, where sigma represents the mode that we're in. Since it's a hybrid plant, we can have different modes. Then we also have a hybrid reference model and auxiliary reference model. We have the same adaptive law, written using pi for brevity. We have the same control law, with the same error-bounding control law. This time, though, the switching mechanism is not around epsilon equal to 0, but around a neighborhood of the origin defined by the user, which is represented by delta. Then we have the switching laws, which tell how much the reference and the auxiliary reference model should jump. Since these models are also hybrid, we can have instantaneous jumps in their state. We will now have a look at some numerical simulations performed using a high-fidelity physics engine to validate the algorithms shown so far. More specifically, we will employ an X-8 copter UAV for performing some missions. So, the first mission is in nominal conditions. We have on the left the proposed control system, and on the right we are comparing it to robust two-layer MRAC, which is the baseline controller from which the proposed control system has been derived. We use this mission to tune both control systems so that they obtain similar results. Here we're seeing the norm of the position and velocity tracking error of the outer loop. In red, we have the proposed control system, while in blue, we have the robust two-layer MRAC controller, and we see that we obtain very similar results. For fairness of comparison, no further tuning will be done to the two controllers for executing the next missions. Mission 2 involves the complete failure of one of the 8 motors of the X-8 copter. On the left, we have the proposed control system that, after the motor fails, is able to complete the mission. While on the right, robust two-layer MRAC is not able to successfully complete the mission. Here we have the plots of the position. We can see on the left in the proposed control system plots at the very bottom. If we zoom in, we can see the resetting events in the reference model represented by the black line, that shows how the switching law acted on the system and how it was useful to stabilize the system. In fact, if you look at the very same thing on the right, for the robust two-layer MRAC Z position, we see that, without the switching mechanism, the vehicle went unstable. Also, another reason for which this instability happened is explained here. The plots represent the thrust of each individual motor of the X-8 copter. So if we look on the right, where robust two-layer MRAC is, we see that after 6.5 seconds there is the failure of one of the motors, and we can see that the other motors reach saturation, which brings to instability. Remarkably, that doesn't happen for the proposed control system. The third mission involves the same trajectory, but executed at the faster speed, and a payload drop. Also in this case, we can see that the proposed control system is able to execute the mission while the robust two-layer MRAC controller fails. Here we have the norm of the position and velocity tracking error of the outer loop, and we see in red the proposed control system able to safely land while the robust two-layer MRAC controller go unstable due to the payload release. We'll now have a look at some experimental flight tests to show the feasibility and performance of these algorithms under real-world conditions. In this mission, the UAV is required to follow a three-dimensional lemniscate trajectory while keeping its roll axis tangent to the trajectory. Here, we are looking at the proposed control system in action. The vehicle tracks a time-parameterized trajectory generated from a sequence of waypoints sampled along the lemniscate curve. A motion capture system is used to estimate the full state of the vehicle during the experiment. The control algorithms run on board on the companion computer, which generates and sends direct motor commands to the flight control unit. The left-hand side plot here represents the position and velocity tracking error norms, while the right-hand side plot represents the respective L2 norms. From both plots, it emerges how the proposed control system, represented in red, yields better performance than the robust two-layer MRAC framework, represented in blue. The left-hand side plot here represents the total thrust required by the UAV, while the right-hand side plot represents the time required to execute both algorithms during operation. From both plots, it emerges how the increase in performance shown in the previous slide is obtained without much difference in terms of control effort or computational complexity. Thank you very much for your attention. For more information, please contact Dr. Andrea Laflito at the email shown here, or visit the website shown here. Finally, we would like to acknowledge and thank the sponsor of our research.